And we're going to transition into the final talk of the session, which is going to be given by Faxing. And it is about a paper titled Notary, Deniable Messaging with Retroactive Avowal. Just waiting a little bit for the slides to come on.
I think we have plugged it in. Oh, should have gone.
You can use this one.
I can use that one. Oh, here. Oh, here we go. All right.
Okay.
Right. This is the very last talk. So approaching to 7. So thank you for everybody here with me. Just a round of applause for you all. So, yeah, I'm Faxing. I'm from University of Melbourne. Today I'm excited to be here to share our recent work, Notary, Deniable Messaging with Retroactive Avowal. This is a joint work with Shannon County, Joseph Bono, and Ria Wabi. So, as we all know, most of the secure messages are deniable. So, suppose Alice and Bob, they're kind of activists, usually participants in controversial activities. So, there's be possible that in the future, Alice might face some allegations in participating in some terrorist activities. So, yeah, her lawyer might suggest, oh, Alice, you can just present your conversation history to say you didn't say this thing or you didn't plan any terrorist activities. So, Alice might consider submit his chatting history to the judge, say, it's not me, I didn't do that. So the problem is an attorney could just say, oh, it's just forgery since you are using deniable messaging protocols, right? So there's no way for judge to tell the evidence that Alice presented is real or fake. So yeah, for Alice, there's no way to debunk it because you use deniability. So how can we help Alice then? Well, we could consider use message frankening. Message frankening is like for one party. So the one party is just like he could just report some harmful messages that he received from Bob to the judge, and the judge will say, hey, you actually send this harmful message. But just with that, we can just say, oh, Bob could help Alice by just sending to using message frankening protocol, say, Alice actually says this, and he's not participating in any terrorist conversation. But this can be abused by Bob terribly. What do I mean is like Bob can say, oh, Alice actually said all those stuffs, and which will definitely broke the privacy and reliability of Alice's message, right? So what we truly want, our question is like we want to retain deniability while we have the options for them to prove what was said. So what we truly want is like ideal protocol is like the two party need to consent to prove, okay, this is our conversation history, we are the source of the message. So this is actually what we mean by, say, avowal. So our result is to combine deniable authenticated key exchange protocol with our new notion, like we say avowable designated verifier proof. So combine them gives us, oh, it should be here. should give us no tree. The first DKR protocol. I don't know what happened here. Oh, it's here. So here's our short list of contribution. First, we propose a new notion, avowable designated verified proof. With that, we can construct the first DKR protocol. We prove our construction is actually UC secure. We implement and say it's actually concretely efficient. So here's our technical map. We first present our observation or trick for us to do how to prove a non-knowledge. With that, we can construct our ADV proofs, and with ADV proofs, leads us to DKR protocol. So before jumping into ADV proofs, let's first recall what is like a designated verified proof. So designated verified proof is just a proof for a very special statement. The statement here is S prime here. S prime is just a statement of disjunction of either S is true or I know Judge Judy's private key. So here we assume that Alice knows the witness to the statement, and Judge Judy, of course, has her own key. One interesting thing about designated verified proof is that both parties can generate the valid designated verified proof. For Alice, he just needs to prove the knowledge of the witness to the statement, and for Judge Judy, of course, just by proving her knowledge of her own private key. Also, another interesting thing that we observed in the designated verified proof is like there's gonna be 3 different views for 3 different people on receiving a designated verified proof. Say Alice, when she gets a proof, she knows that the proof comes from Judge Judy. That's because she knows the witness to the statement. But and of course, Judge Judy does not know this statement. The only way for Judge Judy to give out such a designated verified proof is to prove her knowledge of a proprietary key. So this proof, Alice could of course tell this proof is actually came from Judge Judy. So for Judge Judy, when she gets a proof, she knows this proof came from Alice. The same reason Judge Judy has her own private key. So the only way to generate this kind of proof is just by proving the statement S. Well, the tricky thing is like for the public, there's no way for public to tell the proof came from Judge Judy or not, or S is true or not. So this always gives us a sensibility, deniability, and because both Judge Judy and Alice, they can deny generating the proof. So what do we actually mean by saying ADV proofs, avowable designated verified proof? What we want to say is we want to retain the deniability within the designated verified proof, but we want to enable the provers to later avow. So our idea is to add an additional statement P, which we can bound if proof really proves S. So in this way, we can just convert the statement S prime to S bar. So by proving the S bar, this actually enables like users or prover to later avow by just proving either P or negative P. So our final ADV proof goes like this. First, Alice could just send an ADV proof is of the statement S bar to Judy. Later, when she decides to avow, she can just send a proof of P. Thus, if she can prove P, then we know actually this proof is coming from S bar by proving the S statement S. So how can we do such kind of a proof by proving a negative P, right? Well, here we present a nice and simple trick for us to do prove negative P. So what we call this trick is like we call it proof of non-knowledge. It's work on the discrete logarithm setting with it's a group with 2 independent generators G and H. First, we let Alice sample a random x prime and set y to be the h to the x prime. Then since Y is a group element, so there's definitely gonna be another X which maps the generator G to the Y. So in this way, Alice could just prove, okay, I know X prime. So what she essentially proved is like she actually proves I don't know X. That's because she generated Y from X prime. So there's no way for her to know the X, which is the discrete log of Y to the base G. So here we can know that the non-knowledge of X is actually the instantiation of the statement negative P, and the statement P here is actually the instantiation of knowledge of X. Just a side note, this is a kind of a similar trick that which used in the narrow Pincus oblivious transfer construction. So with kind of the concrete construction of the ADV proofs, how can we get a deniable authenticated key exchange protocol out of it? First, let's recall that ADV proofs already gives us deniability, and it's already gives us Avowal as well. So what we need to do is how can we enable like Alice and Bob that collectively assent to Avowal their message? Well, our way is we just need to secret share the secret in doing the proof of non-knowledge, and with that, how can we? The final step is how can we make it like ADV proof construction in the secret share nature by working under the authenticated key exchange protocol. Well, due to the time limit, I'm not gonna explain it here. If you're interested, please see our paper. So here's just a short performance evaluation. We've shown that regarding the number of messages in the transcripts, it's always constant for parties to avow. So no matter how many messages that they decided to avow, it's always constant for them, both computation and communication. And the computation and communication grows linearly with the judge with the number of messages. So the final takeaway of this paper is like in a deniable messaging conversation, say between Alice and Bob, together with each other's consent, they can convince the judge that a message or specific messages is indeed in their conversation history. With that, I'm happy to take any questions.
We'll take one quick question.
I wouldn't consider myself a cryptographer, but let's say Alice and Bob can both attest a message. And let's say Bob says, I would like to attest, and Alice in court says, oh no, I don't want to attest, then isn't this like already enough to maybe have some circumstantial evidence against Alice that could be negative in a court proceeding or anything?
So what you say is like they can like assign some message to?
No, it's like Alice and Bob have a message history, and Bob says, hey, I would like to show this in court, and Alice says, no, I don't want to show it. Then this fact alone that she like denies to cooperate.
Oh yeah, in this way it's like looks like the message frankening situations that we mentioned. Since if we just want that, we can just use message frankening protocol. With that, but as I mentioned, the message frankening protocol could breaks like the Alice here privacy and deniability. That's why we need like two party to consent.
Okay, thank you all very much for attending. This concludes the messaging session. And let's thank our speaker one more time.